Somewhere in eastern China last year, two solar arrays sat side by side in the same field, under the same sky, catching the same light. One was 3.5 times larger than the other. More panels, more steel, more land, more money in the ground. At the end of the day, the engineers pulled the production numbers, and the smaller array had put out more electricity than the big one. Not marginally more. More. From a system a fraction of the size. The material that did it is called perovskite, and it may be the last real chance America gets to own a piece of its own power grid. Before we get into it, drop your state in the comments. Land cost and roof space change this math completely, and I want to see where this audience actually lives. Here's the part almost nobody says out loud. Right now, somewhere between 80 and 95% of the world's silicon solar supply chain runs through China, depending on which link you measure. The polysilicon, the wafers, the cells, the finished modules. When a crew bolts panels onto an American roof this afternoon, those panels almost certainly pass through Chinese factories somewhere along the way. That's not a talking point. That's the finding of the International Energy Agency, S&P Global, and the Center for Strategic and International Studies. America spent 40 years learning that energy dependence is not an economics problem. It's a leverage problem. We remember 1973. Gas lines, odd even license plates, a president on television talking about national sacrifice. We spent 2 generations and a lot of blood and treasure reducing our dependence on foreign oil. And then, quietly, without anyone voting on it, we built a deeper dependence on foreign sunlight equipment. The US has ramped domestic module assembly considerably in the last few years, and that's real. But assembling a panel in Ohio doesn't make it American if the polysilicon, the ingot, and the wafer all came from overseas. It just means the last step happened here. It's the difference between building a car and putting the badge on it. So let's talk about the physics, because the physics is the whole story. A solar cell works because light knocks electrons loose. Photon in, electron out, current flows. For 50 years, the material doing that job has been silicon, purified at 1400 degrees, grown into crystals, sliced into wafers thinner than a fingernail. Silicon is good at that job. It is also stuck. There's a hard physical ceiling called the Shockley-Queisser limit, the maximum efficiency any single material solar cell can ever reach. For silicon, that's roughly 29%. The best panels you can buy today run around 20 to 23. 50 years of engineering has pushed silicon right up against the wall, and the wall doesn't move. That's not a funding problem, that's physics. Perovskite isn't a substance, it's a crystal structure, an arrangement of atoms first identified in a mineral out of the Ural Mountains in the 1830s. The modern photovoltaic versions are lead halide compounds, and they happen to be extraordinarily good at grabbing light. But here's what made engineers sit up. Perovskite doesn't compete with silicon for the same light. Silicon is best at the red and infrared end of the spectrum. Perovskite is best at blue and green, the high energy end. 2 materials, 2 different appetites. So somebody asked the obvious question, what if you stacked them? That's a tandem cell. Perovskite on top, silicon underneath, each one eating the part of the spectrum the other one wastes. Lab-certified tandem cells have pushed past 34%. Full-size modules, not thumbnail lab samples, have been certified above 34 as well. Perovskite has already cleared the ceiling silicon can never reach. Not in a projection, in certified measurement. The efficiency is impressive, but the manufacturing is what changes the map. Making silicon cells requires furnaces at 1400 degrees, crystal growth reactors, diamond wire saws, and clean rooms that cost hundreds of millions to build. China won the silicon race partly by pouring capital into those facilities at a scale nobody else would match. You can't outspend that decision after the fact. It's already spent. Perovskite is made differently. You dissolve it in a liquid and coat it onto a surface. Slot die coating. Spray. Roll to roll. Temperatures under 200 degrees Celsius. Researchers at MIT and Stanford have deposited these films in open air with no clean room at all. Think about what that means. Instead of a $500 million fab, you're closer to a very sophisticated printing press. If you've ever run a shop, managed a plant, or just watched American manufacturing get hollowed out one line at a time, you understand the significance immediately. The game stops being about who builds the biggest factory and starts being about who owns the process knowledge and moves fastest. America is decent at that game, when we're allowed to play it. The National Renewable Energy Laboratory in Golden, Colorado, has been the world's center of gravity for this research for over a decade. MIT and Stanford have been the incubators, and that lab work has walked out the door into real companies with real payrolls. Swift Solar was founded by researchers straight out of those institutions and has demonstrated tandem technology on a Department of Defense microgrid. That's not a science fair, that's a procurement pipeline. Tandem PV is chasing gigawatt-scale production later this decade. 1 gigawatt runs roughly 190,000 American homes. Kalux took a different and frankly clever angle. A perovskite layer built into glass that sits on top of existing silicon architecture, upgrading the technology instead of replacing every panel already installed. And First Solar, the largest domestic manufacturer we have, with lines already running in Ohio, bought a Swedish perovskite outfit and licensed Oxford PV's US patent portfolio. That's a company positioning, not experimenting. Now let me be straight with you because I don't do hype. Tandem perovskite panels currently run somewhere around 40 cents a watt. Silicon is around 10 to 13 cents. That's 3 to 4 times more expensive today. Anybody telling you perovskite is cheaper right now is selling something. But look at how the money works over a lifetime. A tandem panel produces roughly 30% more power from the same square footage. On a roof with limited space, on a farm where land costs money, on a telecom tower in the middle of nowhere, 30% more output per square foot means less racking, less wiring, less land, less labor per kilowatt hour. And that's before the manufacturing curve does what manufacturing curves always do. Silicon panels cost $76 a watt in 1977. Today, they cost about a dime. That's a collapse of better than 99% in 5 decades. Perovskite is early on that same curve, and most analysts expect utility-scale cost parity somewhere in the 2027 to 2030 range. Durability was the real objection, and it was a fair one. Early perovskite cells fell apart. Moisture attacked the crystal. Heat pushed ions where they didn't belong. Ultraviolet broke it down. Silicon has a 25-year field record in rain and hail and August heat, and you don't get to wave that away. Those problems have been ground down one at a time. More stable interface chemistry, glass-on-glass encapsulation, hermetic sealing at the module level. Some manufacturers are now writing 30-year warranties. Not solved forever, not perfect. But the trend line is not ambiguous. Here's the part that keeps people in Washington awake. China has designated perovskite a core strategic technology under its national planning. They are not asleep on this. There's a live race right now to set the manufacturing standards for the next generation of solar. And whoever sets those standards doesn't just make better panels. They own the foundation layer of the global energy transition, the way semiconductors are the foundation layer of computing. We understood that about chips. We passed a law about chips. We spent billions on domestic fabs because we decided it was too important to leave in somebody else's hands. Solar is heading to the same place, and perovskite is the opening. Not because it's cheaper tomorrow, it isn't, but because it's a different game board. Different patents, different capital requirements, different entry points. American institutions hold a genuine pile of the foundational intellectual property, and that IP is the seed of a supply chain that can't be replicated in a season. There's one more thing about this material that gets underplayed. Because you can coat it onto flexible surfaces, it doesn't have to be a rigid slab bolted to a rack. It can be light, it can bend, it can be laid into building glass, wrapped over a curved surface, folded into a pack a soldier carries. Silicon can't do any of that. It's brittle, rigid, and heavy. Every pound matters to a man carrying gear in a remote position, and a film that unrolls and starts making power is a real capability, not a gadget. Here's the paradox worth sitting with, and I think it's the important one. Cheap solar was a gift. Chinese industrial policy drove panel prices through the floor and genuinely accelerated clean energy worldwide. More got installed because it cost less. That's true, and there's no point pretending otherwise. But cheapness built on dependency isn't the same thing as cheapness built on capability. A cheap panel is a gift right up until the day it becomes a lever, until a crisis somewhere gives the supplier the power to restrict, to delay, to raise the price, to attach conditions. We've seen that movie. We stood in the gas line and watched it. Replacing one strategic dependence with another isn't independence. It's a new hand on the valve. Perovskite doesn't fix that by magic, but it's the first real opening in 20 years where American labs, American capital, and American factories can compete on something other than who's willing to lose the most money fastest. The panels are shipping, the contracts are getting signed, the lines are being built. So here's a specific question, and I'd like a real answer. If you could put a panel on your roof that made 30% more power, took up 30% less space, and was built in Ohio or Colorado instead of overseas, what would you pay for it? 20% more? 50? Or does the sticker price win every time? Because that answer, multiplied by a few million households, decides whether these factories get built here or somewhere else. If this was worth your time, share it with somebody who thinks seriously about energy or manufacturing, and subscribe if you haven't. Real technology, real stakes, no hype, that's what we do here every week. I'll see you in the next one.